Page 4 of differential calculus. The derivative function. In a curve, the slope of the tangents of the function at various points are different. In IB, they say gradients instead of slopes. Sometimes it's possible to define a function, a gradient function, which yields the gradient of the function for any value of x within the domain of f of x. Okay, so like it's possible to have a equation which gives you the gradient at any point on the function. So it's a function of a function. Sometimes the gradient function is read f dashed x and is written as f prime x. In my day, we used to call that f prime of x, but I guess they call it f dashed x. Maybe that's the European thing. Blank, which is the specific gradient of the tangent to f of x at the point where x equals a. That would be f prime of a. Okay. See example 4. Okay. Using the graph below, find f of 2. F of 2, this is just what you've always found in the past. The function at x equals 2. So x equals 2, let's say it's going to be about here. Doesn't really matter because you can see that the function f has the same value, 3, at any x value. So, of course, this is going to be 3. Okay? What about f prime of 2? F dashed 2. F dashed 2 is the slope or the gradient of the function at x equals 2, which is here, right? So what is the slope or gradient here? It's 0 because it's a horizontal line. Okay? All right, number 2. Using the graph below, find the value of the function at x equals 0. Okay, so at x equals 0, the function is equal 4. All right? And then it says f dashed of 0. So this would be, what is the gradient of the function at x equals 0? And that would be not 4, but it would be whatever this inclination is here. And you can see, since it's a 45, 45, 90 triangle, that the slope here is going to be, rise will be -4 and the run would be +4. So the slope here is -1. Okay. Number 3. Consider the graph alongside. F of 2, find f of 2 and f dash 2. So f of 2 would just be this point here, which looks like it's halfway between 1 and 5. Oh, we can also find it because it looks to be a parabola. But let's just guess here. It's like if this looks halfway between 1 and 5, so we would say maybe it's 3. Okay, the height maybe is 3, and f prime of 2. F prime of 2 looks like it is, we just need to find the gradient of this here. So the run here would be 4 minus 1, which is 3. And the rise here would be 5 minus 1, which is 4. Okay, so the slope would be the rise, 4, divided by the run, 3. So the answer here is going to be 4/3. And the answer for this one is going to be 3. Okay. 14e, differentiation from first principles. Okay, this is how you use limits to find the derivative of a function. And the way you do it is just like we've been doing in the investigations. You make an expression for the little triangle, which is, the tangent of the curve. And then you just make a triangle, which is you know, h wide, and then this part here would be like, let's say that this point is your point where you're trying to find the derivative x, and then this point here, of course, would be x plus h, right? So this point here would be f of x, and this point here would be f of x plus h. So if you're going to find if you were going to find the slope of this triangle here, what you would do is you would subtract this minus this, and then you divide it by this minus this, and that's exactly what we get here. Okay, and then what we do is we take the limit as the width of this triangle becomes 0, because that's how you make the chord gradient into the tangent gradient. Okay, so think back to your investigations and think about what you did with real numbers, and then we're just doing it here with variables. All right, write 3 different ways of representing the derivative function. Let's see, this from their book reading, we have what we already know. We have f dashed x. We have also the expression y dash or y prime. And we also have the expression dy dx, which looks like a ratio or a fraction, but actually it's just a notation for derivative. Now they're giving us actual functions to put into this expression here. Okay, so I'm going to draw a little triangle here to represent the gradient for this function here. So the x positions are x and x plus h, right? And then the y positions would be f of x, like we have here, except for f of x and the function is just x. F of x would just be x. And then the function at this point here would simply be x plus h also. Okay? So that is the slope we're trying to find. And so basically we can find that by taking limit as h approaches 0 of x plus h minus x divided by x plus h minus x. So you can see that, you know, basically everything just, these kind of cancel out and you just get 1, right? Which gives you the limit as h approaches 0, this is just 1. Okay, all right, moving on. We're going to draw another triangle. This time the function is 5. So you have x and you have x plus h at the x side of your triangle, and the y side of your triangle, you plug in x into the function, but the function is always 5. So this would be 5 and this would be 5. And wait a second, that's not even a triangle because both y's are the same number. So actually you end up with a flat line. The triangle is not a triangle, it's a flat line. So obviously the limit here as h approaches 0, the y varies, from 5 to 5, so that's just 0, right? So basically the top is 0, so the slope of this function is 0. And if we would have asked you what's the slope of y equals 5, then of course you would say that the slope is 0. Okay? If we would have asked you what the slope is of y equals x, you would look at this and you say, well, mx plus b, the m here is actually a 1, so the slope is 1. So do you see how we're using first principles, or this little triangle, to figure out what the instantaneous rate of change in, or the gradient is, but these are functions that have constant slopes. So you could have done it using traditional methods too. Now we're going to do x cubed, which obviously you cannot do with traditional methods. So we're going to draw a little triangle again. And so we have x and x plus h for the x's, and the y's we're going to have x cubed for the lower one, and for the higher one we're going to have x plus h cubed. Okay, now we're going to do the limit, and this one's going to be kind of complicated. So on the top we're going to have x plus h cubed minus x cubed. And on the bottom, we're going to have x plus h minus x. So at the top, we're going to have, remember the binomial theorem. So it's going to be x cubed plus 3x squared h plus 3x h squared plus h cubed minus x cubed. So you're going to expand x plus h quantity cubed, and then you're going to get all that, this first several terms, except for the minus x cubed. And then the bottom we have x plus h minus x, so we just get h. So for you guys that do not like algebra, this might be kind of a nightmare. So we're going to cross out these two because those x cubed minus x cubed is just 0. And then we're going to see what we have left. So what we have left is the limit as h approaches 0 is 3x squared h plus 3x h squared plus h cubed. And it's divided by h. So now we're going to cross out the h's. H squared. So now we have 3x squared. And we still have the limit, right? The limit as h approaches 0, 3x squared plus 3xh plus h squared. Now do you see, if you plug in the 0 for h, you're not going to get an illegal value anymore. At the beginning, you would have gotten 0 over 0, but now that we've eliminated several terms, we're going to get just 3x squared, because these two terms, 3xh and h squared, are going to become 0, but 3x squared will not. So then you end up with just 3x squared, which in our investigation we found out is the derivative of x cubed. Okay, and that's it for page 4.